Hello everyone and welcome back to the course. Today we are going to keep on diving on operations on set theory, but this time we're going to dive into the properties of such operations. Unlike previous sections, we will introduce precise arguments called proofs, which are tools used by mathematicians to validate their discoveries. We will begin by exploring the properties of the subset relation with formal proofs, and we will start by proving the transitive property of the subset relation, meaning if A is a subset of B and B is a subset of C, then A is a subset of C. We will prove this by taking an arbitrary element X in A, and we will show that this element is indeed in C. Here, you have to analyze that we have a hypothesis and a conclusion, which we have to arrive. The hypothesis is that if A is a subset of B and B is a subset of C, then the conclusion, A is a subset of C. Here, we will provide the proof for the transitive property of the subset relation. Let A, B, and C be sets such that A is a subset of B and B is a subset of C. We need to prove that A is a subset of C. In symbols, we must show that for all elements X, such that X is an element in A, then X is also an element in C. Now, let X be an arbitrary element of A. By the assumption that A is a subset of B, we have that such an element is also an element in B. Now, by the assumption in the hypothesis that B is a subset of C, we conclude that the element X in B is also an element in C. Therefore, we have that necessarily A is a subset of C, because we took an arbitrary element X in A and we proved that this element is also in C. This is an example of a conditional proof where we assume the hypothesis and prove the conclusion. Another property of the subset relation is that if A is a subset of B, then the complement of B is a subset of the complement of A. Now, instead of proving the conditional, we are going to prove the contrapositive, meaning instead of proving that P then Q, we are going to prove that not Q implies not P. Now, remember that these two, the conditional and the contrapositive, are logically equivalent, meaning if I prove one true, then immediately I will be proving the other one true as well. So instead of proving that A is contained in B implies that the complement of B is contained in the complement of A, what we're going to prove is that if the complement of B is not contained in the complement of A, then A is not contained in B. Now we're going to prove the contrapositive statement. For that, we are going to suppose that the complement of B is not contained in the complement of A. This means that there exists an element X such that if X is an element of the complement of B, which also means that X is not an element in B, then X is not an element of the complement of A, which also means that X has to be an element in A. Therefore, X is an element in A that is not in B. Therefore, by definition, we know that A is not a subset of B. Since the contrapositive is true, we conclude that the conditional must also be true. Therefore, if A is a subset of B, then indeed the complement of B is a subset of the complement of A. Another important property regarding set equality involves intersection. For instance, the intersection between A and B is equal to A even only if A is a subset of B. This is an example of an if and only if statement, which requires us to prove both directions. Meaning, if A intersection B is equal to A, then A is a subset of B, and also if A is a subset of B, then the intersection between A and B is equal to A. We will start by proving the first conditional. We will assume that A intersection B is equal to A. Now, by simplification, we know that the intersection between A and B is contained in B. And as A is equal to A intersection B, it follows that A is contained in B. Now, for proving the second conditional, we will assume that A is a subset of B, and we need to show that the intersection between A and B is equal to A. Now, by simplification, we already know that A intersection B is contained in A, so we only need to prove that A is contained in the intersection between A and B. Now, for any x in A, as A is contained in B, we have that such an element x is also an element in B. Therefore, as x is an element in A and B, then by definition, x is an element in the intersection between A and B. As we took an arbitrary element x in A and we proved that such an element is also in the intersection between A and B, then A is a subset of A intersection B. Thus, A is equal to the intersection between A and B. Thus, as we proved that the aforementioned conditionals were true, then the original statement must be true. Therefore, A intersection B equals to A is logically equivalent to A is a subset of B.